So in our previous lecture, we were talking about generalized additive models and trees. Okay, so specifically, we were already at the tree section. Okay, so since it has been about 1.5 weeks since our last lecture, I just want to recap what the tree-based methods are. Okay, and after that, then we'll go into the more sophisticated versions of the trees. So basically in tree-based methods, you partition the feature space into regions, right? So here I show you a very simplified example where you oops, what happened? I apologize for that. Let me go back. Okay, so you partition the feature space into regions, right? So here I show you a very simplified example where you basically have two features, x1 and x2, and after you do the let's say you do the tree-based model, you train the tree-based model. That model will partition that entire region formed by x1 and x2 into these regions, and in each of these regions, you basically have estimate either for a regression or a classification task, right? So for instance, it may well be that in region 1, any data point that falls within region 1, you make a certain value prediction or you make a certain classification, and in region 2, you make another classification or a regression, and so on and so forth, okay? So these are basically what I call classification and regression trees, or CART. You can also call them decision trees, right? So whenever you train a tree-based machine learning model, the main question is always, how do you decide on the partition, right? So in other words, how do I know that for the x1 feature, I would need to partition it at t1 and t3, and for the x2 variable, I need to partition it at t2 and t4, and that these partitions will give me the right model to predict the property, right? So the way that this is done is using some form of heuristic algorithm. So obviously you can, for small problems, you can always find the best partition. So for example, in the example that I just showed you, if it is just two features and you only have a limited number of data points, you can always play around until you actually find the best possible partition in terms of either training or test error, right? Now, in most problems, you are not going to have that luxury, right? So especially if, let's say, instead of just x1, x2, you have like 9 different features and you have thousands of data points, right? So then you basically need some heuristic way of choosing how you split the regions, okay? And one way to do this is using what's called a greedy algorithm. So you basically start with all the data, you choose one of the splitting variables, so let's say x1, and then you find the split point s that basically minimizes your sum of square error, okay? So basically this is your sum of squares, this is the sum of squares in region 1, and this is the sum of squares in region 2, right? So this is the total sum of squares in both regions, right? So this is to find the optimal value of that splitting variable is fairly easy to do, okay? So all that, you basically just do a scanning and then you can find that split point s, okay? And you can just keep repeating and keep repeating this process until you basically grow the tree until such point that you decide, well, I'm going to stop my tree growing at this point, and this is my model, okay? So whenever we talk about tree models, there are the main variable that you're controlling is basically the size of the tree, right? So the larger your tree, the more complex your model is. And if you have too large a tree, basically what you have is overfitting, right? And if you have a tree that's too small, basically you have what? Underfitting, right? So there is some optimal in between the two, some region of optimality between the two, okay? So one way to make sure that you actually have an optimal tree is using what is called cost complexity tree pruning. So For instance, you can grow the tree until it is fairly large. So let's say you decide that, well, I'm going to have at least 5 points in each node. Okay, so I'm going to generate a tree until I have 5 points in each node. And then I just start combining some of the nodes to basically some of the leaves of the tree or some of the branches of the tree to reduce the tree complexity, right? So the way that you do this tree pruning is using this cost complexity criterion. So using the cost complexity criterion, you basically have the same thing, which is your sum of squares, but now you actually have a penalty term that penalizes the size of the tree, right? So if your tree is too big, you basically have a large penalty, okay? So that alpha variable basically controls the complexity of your tree, right? So the larger your value of alpha, the smaller the tree will be, okay? So typically you you use what is called weakest link pruning. In other words, you collapse each of the nodes that produce the smallest increase in your mean square error, okay? And then until you basically minimizes this overall cost loss function, okay? All right, now of course trees can be used for both regression as well as classification. For classification trees, you need to know that instead of your mean square error, you do need to use alternative measures of what is called the node impurity, right? In other words, what's the error within each node, right? So for example, you can use what is called the misclassification error. In other words, how many data points within each node do you misclassify? You can also use the Gini index or the cross entropy. All of them perform roughly similarly, okay? Depending on the type of problem, some of these misclassification measures can be better than others, right? Now, the obvious difference between the Gini index and cross entropy versus the misclassification error is, of course, the misclassification error does not have a continuous first derivative, right? So you see that this is actually a function that actually has this sharp change in your gradient at p equals to 0.5. However, the Gini index and the entropy actually has a is differentiable, right? Or rather has a continuous derivative. So in some instances for optimization, this is actually a preferred node impurity measure, okay? Now, as I mentioned before, trees are highly interpretable because you basically have a tree of decisions, right? So you can draw out the tree and you can understand how the model is coming to a conclusion, right? You will have something that says, well, if this feature is bigger or smaller than this particular value, you make this decision. If this and if feature 2 is bigger or smaller than this particular value, you make this set of decisions, right? So there is always a way to read the tree, okay? However, the fact that you can understand what the model is doing doesn't mean that those interpretations are always scientifically valid, okay? So you of course need to bring in your own domain expertise and intuition to figure out what the tree is doing, right? One problem with trees though is that they tend to be unstable, okay? So sometimes you just change one data point or you add in an additional data, they can actually lead to very, very different results, very different models, right? So this is again an issue. Trees also lack smoothness, right? So at least for the standard categorization and classification and regression tree, right? You can just look at this, right? You see that essentially the tree is essentially a series of step functions, right? So there's a sharp change in the predicted value or classification from one region to the next. there is no continuous change in the value, okay? And also, if you are, for certain types of problems, you may want to weight your classifications differently, right? So for instance, if you have a problem where a false positive is not as bad as getting a false negative, you may actually want to weigh the penalty for false negative much higher than a false positive, okay? All right, so we already went through the example. So in scikit-learn, all the tree-based methods are under the tree package, and you have your decision tree classifier and your decision tree regressor, and otherwise the rest of it is pretty similar to the API is pretty similar to the linear models, right? So you call fit, you can score your training data accuracy, you can score your test data accuracy, you can also export the trees. You do need to remember that the input parameters to your models are different for trees compared to your linear models, right? So for the linear models like ridge regression and lasso regression, you have your alpha parameter or lambda parameter in the case of scikit-learn. But in the classification trees, in the tree-based methods, typically the parameters that you care about is, for example, things like what's the max depth of your tree, what's the minimum number of samples per node. You can also set a cost complexity pruning alpha parameter that basically does pruning of your tree based on the cost complexity criterion, okay? All right, so this is the example problem that we looked at. So basically the example problem that we looked at was something that is very similar to our lab number 2. We were looking at the meta-insulator classification. So here we only use a smaller subset of elemental properties to construct our decision tree. This is just for speed purposes, okay, and to make it easier to interpret. So we chose the atomic radius, atomic weight, the column, the electronegativity, and the row. And then the reason why we chose this is simply because most of these properties are available for almost all the elements. And we also throw out some features that are obviously correlated with one another, okay? So for example, atomic radius and atomic volume, I mean, I don't think I need to tell you that those two must be correlated, right? Atomic volume is just 4/3 pi r cubed, where r is basically your atomic radius, right? So there is a clear relationship between the two parameters, okay? All right, so with the meta-insulator data set, you can see that, well, as you increase the depth of your tree, you essentially get better and better performance, okay, for your training data. So this is not surprising. Just remember, right, for a tree, you can always grow your tree to the extent that you basically have just one data point in every single node, and you essentially have perfect performance, right? So it is always possible to get a performance of 1, okay, just by growing the tree indefinitely. However, for your training data, for your test data, that's not going to be the case. You see that your performance actually plateaus off, right? So quite clearly, we can't do much better than, say, something like 82% or so. In other words, an error rate of about 18%. And we get that at around tree depth of around 12 to 15 or so, okay? Now, I want to note that when you are doing this in your lab number 3, don't worry too much about what's the correct value, okay? So here there is no real correct value, right? Anything between, say, like 10 to 15 are perfectly acceptable answers, okay? I probably wouldn't go to 20 or 30 just because, first of all, the bigger the tree, the more overfitting you have, and also the more expensive it is to calculate your tree and train your tree, okay? So there isn't a exact right answer. There is a range of possible answers, and all that we are looking for is that you are making an effort to get that possible range of answers. Okay, so this is just something to keep in mind for your lab number 3. Okay. So as I mentioned, you can also plot out the tree. So once you plot out the tree, you can actually look at the interpretation. You can look at how the tree is making the decision. So for example, the tree is starting from the mean of the electronegativity and whether it is smaller or bigger than 1.9, and then after that it checks the second ionization energy and so on and so forth to basically figure out what kind of values we are going to assign to what kind of classification we are going to assign to the metal or insulator data set. Okay. All right. You can also interpret the trees using feature importance. Okay, so in the lab lecture notebook example, I actually showed you how to do that. It comes out directly from the training of the tree, and with that you can see which of the parameters actually makes the most difference to your classification or regression problem. So in this case, the mean of the electronegativity seems to feature heavily, right? So this tells you basically what parameters actually matter in making the prediction. Okay. All right. So we also talk about the receiver operating characteristic curve. This is a very common way of plotting the performance of models on a binary classification problem. So as I mentioned before, the dashed line essentially represents the line of random guessing. Okay, so in other words, if you just flip a coin to basically make the classification, this dashed line is your result should be very close to the dashed line. If you have a model that performs absolutely perfectly, in other words, it always makes the right classification, then you basically have this black solid line. Okay, and of course in almost all models that you are working with, you are going to fall somewhere in between these two extremes, and the closer you are to this solid black line, the better your model is typically. Okay, so the way that people usually measure that is using what is called the area under the curve. So this is called the receiver operating characteristic curve, or ROC curve. And the greater the area under the curve, in general, the better the performance of your model. Okay, so this curve is basically a plot of the true positive rate versus the false positive rate, right? Okay, there's also modifications of your cut. So for example, there is something called MAS, which stands for multivariate adaptive regression splines. So in this case, instead of using a flat average for each region, you actually fit a set of linear basis function to each region, and this does deal with some of the problems, like for example the sharp change in value that I've just mentioned. Okay, if you are interested in trying this out for the problems that we are in lab 3, you will have to install a different package called PyEarth. So that is something that you need to keep in mind if you want to play with this. Okay, it is not implemented directly in scikit-learn, right? All right. So that's all for decision trees, right? The next topic in machine learning models, which actually is one of the most important, is ensemble learning, right? And so far I have covered the basics of using a single model, right, to perform a machine learning prediction. So we have covered linear methods, whether we are talking about just your standard linear regression to your ridge to your lasso. We have talked about kernel methods, like where you basically use a k nearest neighbor algorithm. We have also talked about using a tree, which is a decision tree where you split the feature space into regions to make a prediction. Now, in ensemble learning, as the name implies, you are not going to just rely on one single model. What you're going to do is that you're going to use multiple models. So in other words, instead of training one single model, you train multiple different models, and then you average the results in some way to get a better prediction, to get a better performance in your prediction. Okay. Now, so the advantage of ensemble learning is, well, in general, it leads to lower variance, and in many cases, the performance is dramatically improved. Okay. The disadvantage is that, of course, unlike a single model where you can usually interpret the model quite easily, you do lose some interpretability when you are essentially taking multiple models and you're just saying, I'm going to take the average of the predictions of 3 different models. Okay. So here we are going to cover 2 of the most popular ensemble learning approaches, which is boosting and bagging. Okay. I would first note that for at least medium-sized data sets, or in some instances even large data set sizes, boosting has emerged as the optimal model in a lot of cases. Okay, so they are very, very powerful machine learning models, especially when your problem cannot be easily described using a single model. Okay. Now, so when we talk about ensemble learning, none of the concepts that we talk about in ensemble learning is specific to one single machine learning method, right? Technically, you can apply ensemble learning to different kinds of models, okay? You can, for example, say, well, I'm going to combine the results of a linear model with a kernel model with a tree model, and that's one ensemble learning model. But by and large, when we talk about ensemble learning, most of the time we are talking about an ensemble of decision trees. Okay, so that is the most common way in which ensemble learning is used. Okay, all right. Now, so let me start with the first type of ensemble learning model, which is boosting. Right, it is one of the most successful machine learning approaches in the past few decades. The concept is actually very similar, very simple, right? What you do is that you combine many weak learners in a committee. Okay, it can be used for either classification or regression. So when we talk about a weak classification, so it's easier to understand this in terms of classification problem. Okay. So let's say you have a binary classification problem where you essentially only have 2 outcomes, 0 or 1. A weak classifier is basically one where your error rate is only slightly better than random guessing. Okay, so let's say you have a 50-50 chance of head or tails. If you have a classifier that can predict that to slightly better than 50%, that is already considered a weak classifier, right? Now, what you will do is that you will take that weak classifier and you are going to modify the data to create basically a number of different weak classifiers, right? And once you actually have a bunch of different weak classifiers, you then combine the predictions from all of them to make a prediction, okay? And the way that you combine them is typically using what is called weighted majority vote. Okay, so you can essentially think of this as essentially democracy of machine learning models. Okay, so in other words, you are essentially saying, well, what's the vote of weak classifier 1? What's the vote of weak classifier 2? What's the vote of weak classifier 3? And then I'm going to combine all those votes. And then I decide, well, the highest vote, the total vote actually tells me what the result of the classification should be. Okay. Now, unlike your standard version of democracy, where everyone's vote matters exactly the same, here the weight of the votes is typically not equal. Okay. So the weights are usually chosen based on the boosting algorithm, and the algorithm basically figure out what the contribution from each weak classifier should be. Okay. Now, as I mentioned, generally there's nothing that says that this this classifier must be a decision tree, but the most common way in which you apply it is using decision trees as the base classifier. Okay. All right. So let me start with one of the simplest one, which is called the ADA-boost algorithm. Okay. Again, we are going to use classification as the example problem because this is easier to understand. For regression, it is pretty much just a slightly modified version of this algorithm. Okay, so the initial way that the way that the ADA-boost algorithm works is that you first initialize all your weights as basically equal, right? So in other words, if I have n classifiers, I'm going to put a weight of 1 over n to all of them. Okay, and what I would then do is that I will basically iterate through all my different classifiers. Okay, I'm going to fit each classifier to the training data using the weights for all the data equally, by weighting all the data equally. And then I'm going to compute the error rate, right? So the error rate is basically the number of points that are not correctly classified, right? And I'm going to divide this by the sum of the weights. Okay, so for the first round, obviously this is just 1 over n, and this is the sum of 1 over n. So basically you get 1 at the denominator. Okay, and after that you then compute this factor alpha, which is the log of 1 minus the error rate divided by the error rate. And then what we are going to do is that we are going to set the new set of weights as equals to the old set of weights exponent your alpha m times the times your misclassification. Okay, so now this sounds a bit complicated, but the way that you can think of this conceptually is that you are going to weight the points in your data set that are misclassified in your previous step higher. Okay, so in other words, I'm going to increase the weight on the misclassified points so that in the next round, when I retrain my classifiers, those data points are given a higher weight. Okay, so in other words, I'm trying to force the model to improve the performance on the observations that were misclassified in the previous step. Okay, now after you finish going through all the different classifiers, eventually your final output is basically just the weights that you have, all your weights that you have determined multiplied by the prediction from each classifier. Okay, now just to show you pictorially how this works. Okay, so let's say you start at with your original data set here. Okay, and you basically this is your original data set. And the size of the plus and minuses show you basically what's the weight on each data point, right? So once you actually, initially what you're going to do is that you're going to weight all the data points equally. Okay, so you can see that all the pluses and minuses are exactly the same size. Okay, and you are going to train your classifier, right? So let's say your decision tree figure out that there are only 2 regions, okay, just for simplicity's sake. And that 2 regions is given by this dashed line over here. Anything below the dashed line, I'm going to classify it as positive. Anything above the dashed line, I'm going to classify it as negative, right? Now, what you see is that, well, this classification is not great, right? You have a few points that you classify correctly. However, you have these 2 points that were classified wrongly, right? They are technically supposed to be minuses, but they are classified as positives. Well, this positive point is actually sitting on the negative side of the classification, right? Now, what you then do is that in step 2, you are going to go through this compute the error rate. You're going to set the weights alpha, and you're going to set each of the weights differently depending on whether you are misclassified or not, right? So in other words, these 3 points, which are wrongly classified in this round, they are going to be given a higher weight in your second round. Okay, so in other words, now in my second round, when I redo my classifier training, these these three points are going to be given a higher weightage in terms of the error, right? So in other words, the algorithm will be forced to try to get these 3 points correct, while the rest of the points will decrease in weight. Okay, so let's say in step number 2, you basically train a new classifier, and this second classifier basically performs like that. And now you basically have these 3 points which are now misclassified, and you are now going to weight these 3 points more, and then you keep going until you basically get a set of classifiers that have different weights. Okay, so this process basically gives you a set of different weak classifiers, or rather a set of weak classifiers, and eventually at the last step, you basically have essentially a summation of the prediction of all your classifiers weighted by the error performance. Okay, and that basically is the AdaBoost algorithm. All right. Okay. Now let me clear the annotation. Okay. Now, to use these models in scikit-learn, you actually have an ensemble package where all these algorithms have been implemented. Basically, the AdaBoost algorithm is implemented as the AdaBoost classifier. There's also an AdaBoost regressor. I'm going to go to the documentation of that method. Okay, so let me quickly switch my sharing. All right. Okay. So this is basically what you get with your scikit-learn AdaBoost classifier. Okay. You basically see that to initialize your AdaBoost classifier, you need to set what your estimator is. Okay. You need to set the number of estimators. Okay. So this is always a parameter that for ensemble learning, you always have to decide how many weak classifiers are you going to use, and this is a parameter that you need to basically estimate, converge, find what the optimal value of this parameter should be. Okay, so this is a key parameter that you need to figure out. Okay, so typically you use you can specify what's the kind of estimator you can use. As I mentioned before, you can basically use any estimator. This can be a linear regression model, it can be anything, right? But typically, as I mentioned, if you don't actually set the estimator, the default is basically your decision tree classifier. It will be initialized with a max depth of 1 if you don't say anything, right? Obviously, this is typically not the optimal classifier. You usually also want to play around with the depth of your decision tree classifier. Okay. The second parameter that you need to work on is basically your n estimators. Okay. So the default is 50. Again, typically not the optimal value. Okay. You do need to try to increase change the number of estimators to basically get the optimal value of your n estimators. Okay. The learning rate essentially is a parameter that sets what's the weight that you apply to each classifier during each boosting iteration. Okay, when you have a higher learning rate, that increases the contribution of each classifier. So there is always a trade-off between the learning rate and the n estimator parameters. Okay, so you do need to play around with this learning rate as well. Okay. The algorithm basically is what the boosting algorithm is that is used. Typically, I don't bother changing this, but in some instances, you might want to play around with it. Okay. All right. So let me show you an example. So I already pre-installed PyMatGen before the meeting. Okay. Hopefully everything goes without errors. Okay, this is computing the actual data set. I'm sure since you guys did lab number 2, you know that this actually does take a bit of time. While it is computing, let me go to the AdaBoost section. Okay, so in ensemble learning, okay, one of the things that you need to figure out is basically what is the estimator that you're going to use. So in our instance, we are going to just use the decision tree classifier. For the decision tree classifier, you need to decide, well, what's the max depth of the classifier that I'm going to use for classification. Here I'm using 3 for the classification problem, and I'm using 15 for the regression problem. This was just a parameter that was set based on playing around with different values of this max depth. Okay. I'm going to use grid search CV again to basically find the optimal number of estimators. Okay, so as you can see, I am going through the potential values of n estimators ranging from 10 to 100 in intervals of 20. Okay, so in other words, 10, 30, 40, 50, and so on and so forth. And then I'm going to plot the performance of my classification task based on my n estimators parameter, right? And what you see here is essentially as our n estimator parameters increase, we can actually get reasonably good classification accuracies, right? So up to about 70 or 90, you already get a classification accuracy of about 0.3 or so, 0.3, 0.25 or so, okay? So, so you can also play around with the depth of the tree to basically figure out if you can get different even better improvements, okay? But please remember, right, every time you need to evaluate the performance of your model, you do need to do some form of cross-validation, or at a minimum, you need to do a train test split, and you are going to use your test data to evaluate the performance of your model, okay? So the training, I plotted the training accuracy just for reference, but you should never be evaluating your performance of your model based on training accuracy. Is always, as always, the only one that matters is basically your test accuracy. Okay. So, okay. Here, basically, we are using the AdaBoost regressor. So, again, you can play around with things like the learning rate. You can change the max depth. I also did a number of I also try to find the best value of your n estimators using based on these values. And remember that the scoring of a regression problem is different. So here we are using the negative of the mean square error. Okay, so in general for scikit-learn, the higher the value of the score, the better. So negative mean square error means the higher the value of the negative mean square error, the better the performance of your model. Similarly, for something like classification, the higher your accuracy, the better, right? So again, here you actually see quite clearly there's a plateau, right? So once you go to about an n estimators of about 30 or so, you get a plateauing of your performance. Essentially, you get a mean square error of about 0.78 or so, okay, in terms of the error. And that is basically the best performance of this regression problem for now, okay? All right. let me go back to the slides. Okay, maybe I will just stop here for a few seconds. Does anyone have any questions regarding the ADA boost algorithm?
Professor, what is N that you're iterating through? The number of classifications.
This one, the N estimators?
On the previous slide, M equals 1 to capital N.
Ah, okay. So yeah, the number of estimators basically here. So if you are you are essentially in this case this big capital M is the number of estimators in this case. Okay.
All right. Oh,
Any other question? All right. If not, let me move on, right? Okay, so other than ADA boost, there is also another form of boosting algorithm called gradient boosting, okay? So we can think of the algorithm in slide 22 as essentially a forward stage-wide fit of an additive model. So you can see that essentially at the end, we essentially have a summation of a weighted set of classifications, right? So this is classical. If you look at this looks like the generalized additive model to you, right? So the ADA boost algorithm is a greedy approach that seeks to maximally reduce the loss at each step. So in other words, it goes via the steepest descent, right? So we keep adjusting the weights on each data point to try to reduce the loss of the model at every single step. Now, the gradient boosting is a slightly different concept, okay? It is still a boosting algorithm. In other words, we are still doing a stage-wise fitting of models. However, in gradient boosting, what you do is that you fit each new learner to the residuals of the errors of the previous step. Okay, so this is basically how it works. Okay, so let's say in iteration 1, so here we are doing a regression problem. Okay, so it's easier to demonstrate gradient boosting using a regression type problem. Okay, so let's say I have this set of data points, okay, and when I first fit my initial decision tree, I basically get a model that looks like this, right? So anything that falls within this region, I'm making this prediction. Anything that falls in this upper region, I'm making this prediction, okay? Now, obviously this prediction is completely wrong, right? Not completely wrong. Well, it gets it exactly correct for this set, almost exactly correct for this set of data points here. It gets the rest of the points wrong with a certain amount of data, a certain amount of error, right? So what you will do is that you're going to take the residuals, which in other words, what is the difference between the actual value with your predicted value? And you are going to, these are basically what I call the residuals, right? So in other words, what's the error of the prediction, okay? And then you're going to fit a second learner, and this second learner, you basically fit it to the residuals, okay? And then you basically, for example, you get something like this. This is your new learner that fitted to the residuals. And then you compute the residuals again, and then you repeat the process, and you keep going on and on until you basically have a bunch of learners that are fitted to essentially correct the errors, the residual error of your prediction. Okay, so this is basically what's called gradient boosting, right? All right, so gradient boosting is extremely successful. Okay, so far, I would say a lot of the best performing models in the literature, they are some form of gradient boosting. Okay, so you have your standard gradient boosting. There are also modified versions of this gradient boosting. For example, there's something called XG boost, which you may have heard about in the literature. XG boost stands for extreme gradient boosting. Okay, you can read about the details by searching out what XG boost is, but you just need to know that they primarily work on the same concept as gradient boosting. It's just the differences are mostly in the details and some algorithmic implementations. Okay. Now, for gradient boosting, again, they are in the ensemble package. You have both a gradient boosting classifier and gradient boosting regressor. Once again, the key parameters that you always have to figure out are what are the number of estimators and also the kind of estimator that you're going to use to construct your gradient boosting ensemble. Okay. All right. Let me go back to the slides. Okay. So in gradient boosting, you can see that, well, I'm going to use exactly the same. So in gradient, for the gradient, okay, let me go back to this. Okay, so in scikit-learn ensemble, you see that they actually have a bunch of different ensemble packages, okay, models. One ADA boost classifier and regressor we just talked about. You have your gradient boosting classifier and regressor. I'm going to talk about random forest later. There's a few others. I'm not going to go through all of them. It's just simply because there's just too many variations for me to go through every single one. Okay, so I'm going to just click on gradient boosting, and you can see that, well, for gradient boosting, first of all, you always work with tree-based methods. So there's no such. So in this case, you don't actually you can't actually choose what kind of estimator you're going to use. You can set the parameters of your decision tree in the gradient boosting classifier itself. For example, you can set the max depth, the min sample split, the min samples leaf. All these things are things that you can set. Okay, you can even set something like the CCP alpha. Okay, so this basically these are essentially your decision tree parameters that are the same in your gradient boosting tree. Okay, and the key parameter is as always this n estimators and the learning rate. Okay, there's always a trade-off between the two, and you are going to figure out what's the best so-called best value of these two parameters. Okay, so this is the gradient boosting algorithm. You can see that, well, in actual fact, the gradient boosting does give you a slightly better performance compared to your other boosts. So in this case, the accuracy of my classification actually rises up to about 0.83 something. Okay, originally it was 0.82 something, right? So gradient boosting does seem to be achieving a slightly better accuracy. It's not always guaranteed, but in this case, it is actually a better performing algorithm, right? So similarly, you can also do it for regression. Again, you can do a grid search to basically find what's the best value of n estimators. Typically, you also want to try to find the best value of the depth of your tree or the mean samples in your leaf and so on and so forth. Okay, so in the lecture, I'm simplifying the search because each of the search actually takes a fair amount of time. You are going to play around with this during your last lab. So here I'm showing a simplified version where we only search based on one hyperparameter, which is your n estimators. Okay. Okay. Any questions regarding gradient boosting? Oh, I also want to say that if you are interested in XGBoost. XGBoost is not implemented in scikit-learn. You actually have to install a completely separate package. Okay, so it is basically a gradient boosting algorithm is designed to be highly efficient, flexible, and portable. And the nice thing about XGBoost is that so far it has been one of the highest performing models in a lot of different problems. Okay, so if you want to try it out, especially for lab number 3, I will actually highly encourage that you do so. I also wouldn't. I just want to know that I wouldn't expect you to do it in the sense that if you choose not to try XGBoost, I'm not going to penalize you, but it is actually quite useful to go through this XGBoost documentation, where they basically go through the tutorials. They talk about what are boosted trees, what is training loss, and what is regularization, and they show you basically how the boosting actually works, and they even give you some toy examples like, oh, how do I what's an ensemble of decision trees, and how do we actually get to a prediction through boosting. Okay, so very, very useful supplementary information to the lecture notes if you want to go through it. Okay, all right. Any questions regarding gradient boosting before I continue?
That's just a quick question on XGBoost. Is it compatible with functions like grid search and other functions in scikit-learn? Or does it have its own separate functions?
Very good question. Let me actually go back. I have to think that it is. Let me see. If I do not remember wrongly, it is. Because my group members actually use XGBoost as well. Let me see. Yep. You can see they basically, for example, you see they actually use scikit-learn to do model selection. So I would imagine, and their API is very similar, right? You see XGBoost classifiers, you set the n estimators, the max depth, and then you do the fit, you do the predict. So it seems that they do exactly use the same API as scikit-learn. So you definitely should be able to use grid-CV and that sort of thing to basically get your to train your models. Okay.
Sounds good.
Yep. Any other questions regarding gradient boosting? Yeah, I will actually highly encourage you to check out XGBoost, whether you are going to use this for this lab 3 or some other problem you are going to do in the future. Typically, I would say right now it is the most efficient implementation of gradient boosting, and for a lot of problems, especially if your data set size is not huge, it typically will give you very, very good results once you tune your hyperparameters properly. Okay. All right. I want to talk a little bit about the loss functions. Okay, so regardless of what kind of model that we are using, we typically need to think about what kind of loss functions we are going to use to fit the model. So very often, so far, most of the time when we talk about regression problems, we have focused on the mean square, the square error loss. Okay, so in other words, what's the sum of squares? We also did talk a little bit about the absolute error. Okay, so this is an alternative to the sum of squares. The difference between the two, as I mentioned before, is that the mean square error tends to penalize outliers much more severely. Quite simply because if you can just think of it, right? If you have a data point that is actually a significant outlier, this error term is squared, so it becomes very big, right? While the effect is much less pronounced if you are using the absolute value of the difference. Okay, so the mean absolute error is obviously a bit more robust against outliers. Okay, so there are also, of course, other type of loss functions that you can play around with. So for example, there's something called a Huber loss, which basically uses the mean square error for if your absolute difference is less than some small number, but it uses this modified version if it is larger than that number. Okay, so typically I usually just play around with this too. I very seldom go around messing around with other kind of loss function, but depending on the type of problem that you are playing around with, you may want to try them out. Okay, now whenever we talk about classification, one very common class of classification problems is binary classification, right? So binary classification just means that you only have two outcomes, right? It's either A or B, and typically we represent those two classifications with the levels -1 and 1, okay? So if my binary classification has those two levels, and the decision boundary is quite simple, right? It's basically at 0, right? If I make a prediction that is greater than 0, it is a classification of 1. If I make a prediction that is less than 0, it is a prediction of -1. Now, as I mentioned before, using the square error does not make sense since we only care about whether it is greater than 0 or less than 0. So very often what we do is that we uses the exponential loss, right? So the exponential loss basically is given by this function over here, is the exponent of negative of the margin, right? The margin is y multiplied by f of x, right? So you can see that the margin is positive if you make the correct classification, right? So if you predict y to be 1 and the actual y is 1, this is a positive value. If you predict f of x to be -1 and your y is -1, this is also a positive value, and you have exponent to the power of a negative of a positive value. In other words, it will be close to 0, okay? And it doesn't matter how big that margin is going to be, okay? You will just go towards 0. However, if you make a misclassification, you see that this number y times f of x becomes a negative number, and then your loss then increases substantially. So this is a loss function that penalizes the negative values a lot more than the positive values for the margin, okay? So so this is a very typical loss function that we use for binary classification. You can also modify it to calculate what is called a binomial or multinomial loss. This is basically used for problems where instead of just a binary problem where you just have -1 and 1, you can use it for problems where you have k different classifications, okay? All right. So I think I've shown you this slide before, so I just want to reiterate what are some of the loss functions that you need to play around with when you are doing your final lab, okay? All right, now I'm going to go to the last type of ensemble learning model. It is basically a bagging model, right? And the classic version of the bagging model is called the random forest, okay? So random forest obviously takes its name from the fact that you have decision trees and you have a bunch of trees, so essentially you have a forest, okay? So the concept of bagging is very simple. You just basically, unlike boosting where you essentially are trying to iteratively build classifiers that are fitted to the residuals or to weight the different data points differently, in random forest model, you are essentially just trying to do averaging, okay? You are trying to average many noisy and unbiased models, and what you hope is that the eventual model actually reduces the variance, okay? So in random forest, is conceptually quite simple. You just grow a certain number of trees at random, and then you just average the results, right? And then in classification, you maybe use the majority vote. So for example, if your B trees, most of them actually say classification is 1, then that would be your answer. If it is -1, that's the answer. In regression, basically what you do is that you take the mean of the predictions from your number of trees, okay? So the way that you grow the trees is that at each branch, what you will do is that you select m variables at random from your total number of p variables. You just determine the best split among the m variables, and then you split that node into two, and then you keep repeating on that tree until your minimum node size is reached, and then you do that for every single different tree in turn. Okay, so and that's basically pretty much it for your random forest model. Okay, so just to show you how it works, so for instance, you have one random forest model, you have 3 different trees, and each tree you split it into different branches by selecting m variables out of your p different variables, and then you do a split, and then you do a further split, and you keep growing the tree until you reach your minimum size, and you do this for all the different trees, and then what you do is that you just basically do majority voting or averaging to get your final prediction. Okay, very, very simple concept, the random forest algorithm. Okay, all right. So I just want to show you an example where we actually use this random forest model. Okay, so this is actually work from my group where we basically we were trying to develop an machine learning algorithm that can take the measured X-ray absorption spectra, the KH ZANES, okay, the KH X-ray near H spectra, and what we are trying to do is to build an algorithm that can directly go from the spectrum to predict what the coordination number and coordination motif of an ion is, right? So in other words, just looking at the spectra, can I know whether do I have lithium in a tetrahedral or do I have lithium in an octahedral or do I have some other ion in a cubic site, and so on and so forth. Okay. This is basically the performance of all the different models that we try. We try a k nearest neighbor algorithm. We try a random forest. We try a convolutional neural network. We try a MLP, which stands for multi-layer perceptron. In other words, a simple feed-forward neural network. We try a support vector classifier. This is a topic that we didn't go through in this this class. Okay, but you can see that out of all the different models, the best performing model actually turned out to be the random forest model. Okay, so this is one example, one actual material science example where a random forest model was used and it turned out to have the best performance among all the different types of models that we tried. Okay, neural networks we will cover in the next lecture. Okay, so let me go to the final set of examples in Google Colab. Oops, why did they reboot my, okay. I am going, okay, so this is the code example for random forest. It is actually very boring here. Okay, there's nothing much to show you. It's quite simply the initialization is the same. Again, I'm doing the grid search CV to find out what's the optimal number of estimators for my random forest model, and you can see that actually as I increase the number of estimators, I get some variation in performance, and I have to figure out what's the best performing model is. In this case, actually, the random forest model actually underperforms compared to the gradient boosting algorithms. Here, my best accuracy is about 0.78 or so, while my gradient boosting actually got up to about 0.83 or so. Okay. In the regression problem, the performance also tapers off after you increase your n estimators to about 10 or 15. I note that this is actually a very simplified problem. We don't have that many features. In many problems, you will see that sometimes your n estimators go up to the hundreds to basically get good performance. Okay, so that's basically pretty much it. Okay, and again, for your boosting algorithms or your random forest models, you can also do a feature importance plot. Okay, which shows you what are some of the parameters that contribute the most to the prediction of your meta-insulator dataset or the band gap in this case. Okay. All right.